Today we are going to discuss a very important equation which is called Poisson's equation. First of all, we will see what the Poisson's equation is, and after that we will solve this very important equation. So let us see first of all Poisson's equation in its original form. As you know, from microscopic form of Gauss law in electrostatics. So according to microscopic form of Gauss law in electrostatics. We know this law in microscopic form is divergence of E, which is equivalently written as del dot E is equal to rho over epsilon naught. In this equation, the different quantities you know very well. Here E is the electric field, or you may say electrostatic field. This is electrostatic field, and rho, this is volume charge density of the charge distribution. This is volume charge density. Epsilon naught, this is permittivity of free space. Of free space, which is an absolute constant. Now, if we want to relate this electric field vector E with the corresponding electrostatic potential, then what is the relation? So you may write, if phi be the electrostatic potential, then we know that the electrostatic field is equal to simply the negative gradient of electrostatic potential. So we write E equal to minus del phi. Now let us substitute this value of E in the above equation, that is Gauss law in microscopic form. So we will have divergence of E, that is del dot E, and we will write minus del phi in place of E, and this is equal to rho over epsilon naught. And what will be this? This is simply del square phi equal to minus rho over epsilon naught. And this very equation is known as Poisson's equation. This is say equation A, and this is called Poisson's equation. One thing we should note here, that this equation is applicable in the region where electric charge is distributed. and in absence of electric charge distribution, this equation simply reduces to Laplace equation, which we have already discussed. Now we will see the solution of this equation. So now solution of Poisson's equation. Solution of Poisson equation. Let us, to solve this equation, we consider a volume charge distribution. Let us see here. We will consider a closed surface S which bounds a volume, let us say tau, and in this region electric charge is distributed. For convenience, I am just assuming that the charge distribution is continuous, and we consider a point which is actually a test point, and a small volume element of this charge distribution. This is just a small volume charge distribution. Say this is d tau, and here is a point O, and distance between O and say this point inside the elementary volume is P, and its coordinates are x prime, y prime and z prime, let us say, and we consider a test point inside at near the point O, which is in fact say the coordinates are x, y and z. This is also a point where we have to find the potential if the charge distribution is given, and you know the charge I have assumed is distributed in this region in continuous manner. Now we will write first of all the Poisson equation. So you know the Poisson's equation is we can write this equation as del square phi of x, y, z. Here phi is a function of x, y, z, where x, y, z is the coordinates of the test point, and this is equal to minus rho. Rho is the source charge, and we have considered a point P inside the source charge whose coordinates are x prime, y prime and z prime. So rho is a function of x prime, y prime and z prime, and over epsilon naught. Say this is equation 1. In fact, in order to solve this equation defined in equation 1, we use Green's theorem, which states that for any two functions of space coordinates, say phi and psi, which are finite continuous and have first and second order derivatives, what the Green's theorem says. So according to Green's theorem. Green's theorem states that volume integral over the volume tau phi del square psi minus psi del square phi d tau. This equal to integral over the closed surface S phi del psi, that is gradient of psi, minus psi del phi dot ds. This is actually the mathematical form of Green's theorem in space. Here phi and psi both are functions of space coordinates. This phi is a function of x, y, z, and at the same time this psi is also a function of x, y, and z. Actually, this existing problem may be dealt as if we are given the function rho of x prime, y prime, z prime. As you see here, we will see here that this rho will be given and we will have to find this potential phi. This is our problem. So in fact for a fixed point, suppose x, y, z, the fixed point whose coordinates are x, y, z, there will be a variable point whose coordinates are x prime, y prime, z prime, over which integration are to be performed. So for solving this equation, that is equation number 1, which is Green's theorem, which is actually Poisson's equation. So let us choose for solving equation 1. We choose psi equal to 1 over r. We select psi equal to 1 over r and see from figure what will be this r, where you can write this r is equal to x prime minus x square plus y prime minus y square plus z prime minus z square whole to the power half. It is evident from the figure. In this condition, our equation 2 will become what? So in this condition, equation 2 will become, we will simply replace by the function psi of the function psi by psi equal to 1 over r. So what will be our equation 2? See this equation. Here psi will be replaced by r, here psi will be replaced by r, here psi will be replaced by r, and here psi will be replaced by r. So replacing all the size with 1 by r, our equation number 2 will become what? Our equation will become integral over tau phi del square 1 over r minus 1 over r del square phi d tau, and this is equal to integral over the closed surface S phi del 1 over r minus 1 over r del phi dot ds. Say this is our equation number 3. Here we see that as psi is equal to 1 over r, so at the origin means where r is equal to 0, psi will tend to infinity. So in this condition we must exclude the point r equal to 0 during our integration, and for this we actually surround the point O with a small sphere. See in this figure, we will surround point O by a small sphere and say the radius of this sphere is r, and we take an outward going normal, say this is n hat. In this condition, if we surround O by a small sphere of radius r and apply then equation number 3, which I have written above, in this equation 3, then the volume tau is then bounded externally by the surface S and internally by S1. You can see here in this condition, this volume tau will be surrounded externally by the surface S, and this is surface S1 say, which is actually a sphere of radius r, and so this volume tau is then bounded externally by S and internally by S1. The outer normal to the boundary surface is n. Here I am just shown in this figure. This is vector n hat, which is directed toward O. And now after this assumption, now we will simplify equation 3. First of all, see the value of del square 1 over r. This is actually 0. Actually 1 over r is this 1 over r actually satisfies Laplace equation, and this will be 0. But how? You can see it very easily. We know that del square r to the power n, this equal to n times n plus 1 r to the power n minus 2. And here in this problem you can see that n is equal to minus 1. And if we will put a minus 1 at the place of n, this result will be 0. So this is 0 for n equal to minus 1. So you can write this del square 1 over r is equal to 0. And now I have assumed a surface S1, which is actually a spherical surface, and on this surface we will evaluate the term gradient of 1 over r dot ds. What will be this? So over the surface S1. Remember, we are talking about the surface S1. So over the surface S1, now we will evaluate del 1 over r dot ds. And what will be this? Remember here, del r to the power n, this equals n r to the power n minus 1 n r hat. Here again there is 1 over r, it means n is equal to minus 1. So when n will be minus 1, then what will be this result? This will be simply minus r to the power minus 2. So we can write it that this is minus 1 over r square n r hat dot ds. And ds is the elementary area vector, and its direction will be just in opposite to this nr. So this will be 1 over r square ds n r hat dot n r hat. And so this is simply ds over r square, ds over r square. Now again we will evaluate the another term, that is del phi dot ds over the surface S1. So evaluate this term, del phi dot ds. I am just going to evaluate this term over the surface S1. Here del phi, this will be simply del phi by del r n r hat, and dot, this is minus n r hat ds. Vector ds is directed along minus nr hat, and so what will be this? This will be equal to minus del phi by del r ds. So you have seen that I have evaluated two terms over the surface S1. But now we will evaluate the gradient of 1 over r over the surface S. So at the surface S, del 1 over r, this will be actually equal to del r 1 over r dot n r hat, and this will be what? This will be simply minus r over r cube, minus r over r cube. So substituting these values in equation number 3, what we will get? So now equation 3 will become, see the equation number 3, you can see this first term will vanish because del square 1 over r is 0, and in RHS we will take the surface integral over the sum of the surfaces S and S1. So now our equation will be actually minus 1 minus integral over tau 1 over r del square phi d tau. This because first term in LHS will be 0, and this will be equal to integral over S1 phi del 1 over r minus 1 over r del phi dot ds and plus integral over S, and again we will write the same term phi del 1 over r minus 1 over r del phi dot ds, and you can write this RHS of this equation seriously, and in next page I will write the different values in the light of the values obtained above. So we can write this. So this will be equal to what? This will be integral over S1 phi ds over r square plus integral over S1 1 over r del phi by del r ds plus integral over S minus r over r cube phi minus 1 over r del phi dot ds. See, the values obtained above have been just put in the RHS of the result. Or you may write it that this is integral over tau del square phi over r d tau. As in LHS there was a negative sign, but I have dropped the negative sign, so let us put the negative sign in RHS and our result will become what? This will be minus integral over S1 phi over r square ds. This is this term minus integral minus integral over S1 phi integral over S1 1 over r del phi by del r ds. And here both terms are negative, and so after putting the negative sign this will become positive, and this will be integral over s r over r cube phi plus del phi over r dot ds, and say it is equation number 4. Now I have assumed a sphere having center at O. You see the figure in first page, and we have assumed that its radius is capital R. So on the surface of this sphere, this small r will be equal to capital R. In that condition, we will evaluate the first two terms in RHS of this equation. So on the surface of the sphere, this r is equal to capital R. So in this condition, integral over S1 phi over r square ds, this will be equal to 1 over r square. We will replace small r by capital R, integral phi ds, and this is actually 1 over r square times 4 pi r square capital Phi, and this will be actually, this r square will cancel out, this will be 4 pi capital Phi. This capital Phi is the average value of small phi on the surface of the sphere. I will just write it down after evaluating the second integral. So again we will have integral over S1 1, now would like to evaluate this integral. So this is integral over S1, 1 over a small r del phi by del r ds. And this will be what? This will be 1 over capital R integral del phi by del r ds. And this will be again integral of ds will be 4 pi r square over r times del capital phi by del r. And this 1r will cancel out, and so this integral will be simply what? This is 4 pi r times del phi by del r. As I have told you previously that this capital phi is what? This capital phi which I have used here is the average value of small phi on the surface of the sphere. On the surface of the sphere. So, in the light of above equations, now we can write equation 5. How you can write equation 5? See, not equation 5 but equation number 4. Just I have evaluated these first two integrals on the surface of the sphere of radius capital R. So if we will substitute these values in this equation 4, then you can see that equation 4 will become what? So now in the light of above values, we can write equation 4 as what? We will write equation 4. This will be, see the equation 4. This is integral del square phi over r d tau, and this will be actually equal to minus 4 pi this capital phi minus 4 pi r del phi by del r, and plus integral over s r over r cube phi, this is a small phi, plus 1 over r del phi dot ds, and say this is equation 5. Now if we now let the sphere of radius capital R shrinks, and so after shrinking it will reach just to the point O. In that condition, the average value of potential on the surface of the sphere, that is capital phi, will be just potential small phi at the point xyz. So you can write, if we now let the sphere shrink down to the point O, then what will happen? Then this capital phi will tend to actually phi at x, y, z, and at the same time the sphere will just change into a point, so r will tend to 0, and therefore in this condition you may say this 4 pi r times del phi by del r, this will also tend to 0 because r tend to 0. And so in this condition, if we will impose these conditions on this equation 5, what will be now the equation 5? You can easily write it. So now you can write, so equation 6 reduces to now this equation will reduce to integral over tau del square del square phi over r d tau. This will be equal to minus 4 pi phi plus integral over s r over r cube phi plus 1 over r del phi dot ds. And from this result we can find this phi. So what will be this phi? This phi, you can see the algebra, this is minus 1 over 4 pi integral over tau del square phi over r d tau plus 1 over 4 pi integral over s phi r over r cube plus del phi over r dot ds. And equivalently we can write this phi xyz equal to 1 over 4 pi epsilon naught integral over tau rho of x prime y prime z prime over r d tau prime. Not prime, but simply you should write d tau plus 1 over 4 pi integral over s, this is del phi over r plus phi r over r cube dot ds, and say this is equation A. Here is ds I have just written ds instead of it. In first term, I have just used the Poisson equation. See this term, del square phi in accordance with Poisson's equations is minus rho over epsilon naught. So I have just used the Poisson's equation in this first term. And from this expression, we can see that the potential phi of xyz can be calculated when the source charge rho is given. And along with rho, we also know the potential phi and its gradient. Then we can find the potential phi at the boundary surface. Now actually in this condition there are two particular cases of interest. So now we will discuss the two cases. So first case first. In first case actually we assume a region bounded by the surface S which contains no charge. That is when the region bounded by S contains no charge. If no charge is contained by the surface S, in that condition this rho will be 0. In this condition rho will be equal to 0. And so this equation A will reduce to what? First term will vanish, only we are left with the second term. So in this condition you can see, therefore phi x y z will be equal to what? This will be simply 1 over 4 pi integral over S del phi over r plus phi vector r over r cube dot ds. This will be the potential, or you may say the solution of Poisson equation when there is no charge bounded by the surface S. You can see it is apparent that the surface integral in this equation B represents the contribution to the potential phi of all charges which are exterior to S. Because we have considered there is no charge inside S, it means uh, what is the source of what kind of charges are the source of this potential? Definitely, as there is no charge inside the surface, so this potential is only due to the charges outside of the surface S. So if the values of phi and its normal derivative over S are known, you know this phi and its normal derivative means del phi, you know, then the potential at any interior point can be determined by integration. So you can see that this potential is only due to the charges exterior to S. This potential is only due to the charge exterior to S. Now we will consider the second case, which is in fact the most important case. In this case, we consider that the region bounded by surface S contains all the charges. It means there is no charge outside of the surface. So when all charges are inside S. In fact, in this condition, we can arrive the actual result by a supposition. Let us consider the volume tau, which is just a finite volume. It is expanded, and so that all the charges will include in it. When it means we consider all the space, so that no charge will be outside of the space, because our condition is there should be no charge outside of the surface S. This will be possible only when we assume that the surface S is infinitely large, and in this condition our volume tau will be in fact extended to all space. It will be expanded to all space, and in this condition you can see that the term potential phi is actually proportional to 1 over r, and del phi, this is of the order of 1 over r square. Then the surface integral actually will be of the order of, because surface integral contains product of phi and del phi. So you can see that the surface integral this will be of the order of 1 over r cube, and area is proportional to r square. So whole of the integral, if we will multiply these, will be proportional to 1 over r. Hence the whole integral will be of the order of 1 by r. And as we are now considering all space, so r actually tends to infinity. So in case of all space, r tends to infinity, and in this condition the integral will reduce to 0. and so the volume integral will tend to 0. That it means that this volume integral will be 0. So contribution of the surface integral so the surface integral, not volume integral, so the surface integral will tend to 0. And you may say there is no contribution of the surface integral in the volume integral in this condition, and hence, as we know, the volume tau now tends to all space. So in this limiting condition, our equation A will now reduce to what? So in this limiting condition, equation A reduces to, this will be phi xyz, and this is 1 over 4 pi epsilon naught integral over all space rho of rho x prime y prime z prime over r d tau. This will be the solution of the Poisson equation. Or you may say that this phi xyz will be equal to minus 1 over 4 pi integral del square phi over r d tau. As we know from Poisson's equation that del square phi is equal to minus rho over epsilon. So you have seen what is Poisson's equation and how we can solve it.